This chapter will get you started with modeling. Now you've just seen that R is very good at manipulating data and creating graphics. R is also very good at doing machine learning. This tutorial will get you started. To begin, it's useful to have some background in terms of terminology. Just like learning any type of language, when you start, you first need to know some vocabulary. If I'm learning Spanish, I need to just know what different words are. Before I can even begin to try to learn, I need to know that tierra means earth, or that fuego means fire. Then once I have a basic vocabulary, I can begin to fumble around and learn the language. In the same way, when you're learning the machine learning language, it's useful to just have some basic vocabulary before you dive in. Now, this gets confusing because there are a lot of different words in data science that really mean the same things. I might say observation or record, but they both mean the same thing. They both refer to the single unit of analysis that we are operating on. The number of observations will always be the value of n, and the number of columns in the data will always be called p. This is also known as the number of features or the number of predictors. The thing that we're trying to predict can be called either the target, the response, the label, the dependent variable, or the outcome, depending on who you ask. We'll also sometimes just call this y. Why? I don't know. This could be either a whole number, in which case we're doing something that's called regression, or it can be a category, like red, green, blue, or yellow, in which case we're doing something that's called classification. For example, let's say that you're a health insurance company and you want to set premiums for a group of people. The premiums for people who are likely to incur high-cost claims need to be higher than the people who are not going to have any claims, or else insurance will not work. Let's use inputs, such as the person's age, their sex, their body mass index, and so forth, and predict what their claims will be. In modeling notation, we would say that these are the predictor variables and that the response is the claims. There's some notation that's useful. We'll talk about single numbers and also vectors of numbers. Vectors are always bold-faced characters. We'll also deal with matrices. A matrix is an array. You can think of a matrix as a table or a spreadsheet. Each item in that matrix is indexed with these subscript characters. If you read the elements of statistical learning, it will always refer to these two special things: the target, which is y, and the approximation of that target, which is called y hat. This is the prediction of your model. This is always a function of the data x. So f is for function, and the function is operating on the matrix x. So here, if I had like two columns in this data, like let's say this first column was age, this first column was sex, I would say that the target the model's prediction is a function of those two columns. The model's never going to be perfect. There's always going to be an error. That error is going to get smaller as the model gets better, but it's never going to disappear. This is always notated as epsilon for error. There's something called a residual, which is the difference in the actual prediction and the model's prediction. The text elements of statistical learning will go into a lot more detail. The first type of model that we're going to look at is called ordinary least squares. This is also just known as simple regression. As the name implies, this is the simplest type of model that is possible. It says that the response is a combination of all the inputs when you multiply them by some numbers. So if I take my input, let's say my inputs are age and body mass index. Say they're just two inputs. Then the output would be, the person's age times 5 plus their body mass index times 10 plus some other number. And it will do this for each person. This is called a linear combination. In a two-dimensional case, this is simply a line that connects points together. On the x-axis, you see, the predictor variable, which is just x, and on the y-axis, you see the response. So these dots are the actual data points. This person might, have x equal to 0, y equal to negative 0.8, but their predicted value is here in the red line, which is, x is equal to 0, y is equal to about negative 0.1. Now, we actually get into a concept that's called expected value. Expected value means that we are not just predicting a single number, but we're predicting a distribution of numbers, a whole collection of things. The way that we talk about this is in a probability distribution. Everyone's familiar with the bell curve. The bell curve shows the range of possible values, right? So the line of best fit is actually predicting a bunch of expected values. For each person, we say that the expected value of the target is equal to some linear combination of the inputs. That means that these predictions we know are not going to always be straight on the line. However, if we did this experiment many hundreds of times, we fit many hundreds of thousands of models, overall, we would see a pattern emerge. And that pattern would correspond to these distributions. If we looked at the average of each point after fitting many different models and running this experiment many times, we would see that the average is on top of the line, even if each point is not. Now, we know that our models are going to be wrong. All models are wrong. Our question is, how wrong is it? There are different ways of measuring this. Generally, we're going to use what's called a loss function. This basically tells us how bad our model is. We want to make our loss as minimal as possible. The most commonly used type of loss function is called the residual sum of squares. This is also called the squared error loss, or just RSS, or even the L2 norm. When RSS is small, then the predictions are close to the actual values that is fit. You can see that just by looking at this operation. You're taking the sum. Well, first, for each observation, you take the difference, then you square all of those differences, and then add them all together. When you replace the y hat here with the linear model and do some fancy math to take the derivative of beta and set it equal to 0 and solve, you could find optimal values. You don't need to ever do this by hand because the computer will always do it for you. So this is an example of how we've taken a problem of statistics and we've translated it into something that a computer is very good at. The computer can always solve the optimization problem. Now, if you've taken a course on regression before, you will be familiar with something that's called a log transform. When you apply a log transform of y, now there are some other technicalities around applying transformations to the response variable, applying transformations to the input variables that we don't need to focus on in this video. For more information, I would recommend reading the Introduction to Statistical Learning, as well as reading this textbook. So let's fit our first model. Let's use the health insurance data set. And let's say that we want charges to be the response, and we want to predict charges using the BMI, the age, and the sex variables. We press run here, and now I want to type in model to look at my model. And this gives me coefficients, the intercept, the coefficient on BMI, age, and sex male. So this tells me that, this gives me a recipe. It tells me how I could make a prediction from the model. If I had someone whose age was equal to 10, whose BMI was equal to 4, their prediction would be 10 times 243 plus BMI is equal to 4 times 327. And let's say that they were male, so I had to add 1344, and then I had to add the intercept minus whatever, 7,000, and that would be the person's prediction. Now this is just a gibberish number, negative 1918, because I just made up those numbers. But that's how a linear model works. If I want to know how the model did, I use the summary function. This will give me statistical insight. This tells me about the residuals, the coefficients, as well as some other statistics. So the most important things to look at here are the estimates of the coefficients here. So you can see the estimate of BMI is 327, and age, and so forth. And also the p-values. So the p-values are a way of telling you if the variable is useful. If it's something that is helping the model to make a better prediction, then you want to include it. If it's something that's not helping the model, you don't want to include it. When the p-values are very small, it means that you reject the null hypothesis that says that coefficient is equal to 0. When the p-value is large, it means that you don't have enough evidence to support using the variable in the model. R has some nice notation. These different stars tell you the relative significance level. If there's only one star next to a variable, it means that the p-value is less than 0.05. So you can see sex male has a p-value of 0.031, and that has one star. Age, though, is more significant, and so it has a smaller p-value. The other insight is from the residuals. This tells you the median residual, the max, and the min. Ideally, you want the median to be close to 0, because you want your model to be overestimating as often as it's underestimating. And you don't want to have like really extreme outlying values, which means that you want your max and your min residuals to be reasonably small. This also gives you the R squared estimate. R squared is a way of measuring the performance. When R squared is close to 1, it means that the model is accurate. When R squared is very small, it means the model has a lot of noise. It's not very accurate. This model's R squared is only 0.12, which is very low. Whenever we're doing machine learning, we're going to want to divide up the data into a training set and a validation set. This lets us fit the model on a blind. Whenever we're doing machine learning, we're going to want to divide the data up into training and test sets.